We don't have this. Oh no. Oh yeah. So we just put it back, we'll get the same result of this, but we can check this out. So you'll see Q2 equals y P2 to the power of sigma. Here in the denominator is negative sigma, but to the numerator, this will be P2 to the power of sigma, just like here. And P1y, 1 plus sigma, P2 to the power of 1 plus sigma. Okay? So this is how we derive Q2 star. And Q1 star is not difficult here. Since Q2 star looks like this, and Q1 star is P1 over P2 sigma Q2 star. So it would be P1 over P2 sigma and P2 sigma y P1 1 plus sigma plus P2 to the power of 1 plus sigma. And you will see P2 can be cancelled, right? So it becomes now P1 sigma y, P1 1 plus sigma plus P2 1 plus sigma. Okay? So precisely the solution here is the same, right? So how to derive Q1 and Q2? Actually, you need these three first order conditions. And the second and third, it looks like a little bit complicated, but you may just leave them here and it will be cancelled very soon, right? So to derive this condition is not that difficult as you imagine. Not that difficult. So you just a little bit be patient to derive the term from here to here. Okay, just be patient. And you do not have to write the whole thing. You just give it a sign here, a symbol here, so that they will be cancelled very soon, right? We have this and rearrange by this. And then we may derive, we have this from here, here, and here. Put it or replace it back to the budget constraint. So we have this, and quickly we have Q2 star. And go back to this, we have Q1 star. Okay? So the whole thing is a little bit complicated, but not that difficult for you, as you imagine. Okay? You must trust in yourself, believe in yourself that you can do this. You have the ability to solve this kind of problem. Okay? I wish you may be more self-confident on this, or on everything actually. And now let's have a look at these two functions. So Q1 is the demand function for a good one. And you will see y here. You see y here. So Q1 must be a normal good. Is that true? Y must be a good one is a normal good because the more income you have, the more quantity demanded. Okay? And now, rho is less than 1. Since rho is less than 1, so rho minus 1 would be negative. Okay? Rho minus 1 must be negative. So sigma is negative. Okay? By assumption. So we just constrain rho to be less than 1. And later on, I'll give you a reason why rho is less than 1. Okay? Now, what do you think? If rho is less than, sigma is a negative 1. But what about 1 minus sigma? 1 plus sigma. What about 1 plus sigma? 1 plus sigma equals 1 plus 1 over rho minus 1, right? So it would be rho minus 1 and rho minus 1 plus 1, so it's rho. Okay? And this will be a negative term. And what about rho? Is positive or negative? Are you sure? Rho is just less than 1, but it is not necessary to be positive, right? It can be negative. We just regulate. Rho cannot be 0, but we don't say rho cannot be negative 5, minus 10. Okay? We just require rho to be less than 1. Okay? So this term can be positive or negative. But it doesn't matter. Why I said that it doesn't matter? Because okay, actually it matters a little bit. But here, let's have a look. Now, Q1 is a function of y. Not only y, but also P1, okay, and P2. So let's have a look at the property of this CES Q1. Under the CES utility function, let's check the property of the demand function for Q1. Okay? And the first property we like to check is the law of demand. What does it mean by the law of demand property? It means partial Q1 star, partial P1, we expect to have a negative result, right? And now we would like to check, can we just get this result? Okay, so Q1 star here. Let's differentiate this term with respect to P1. So we have a P1 here, we have another P1 here. So the first thing is to square the denominator term, okay? So it will be P1 1 minus sigma plus P2 1 plus sigma and to the power of 2 squared. And we differentiate, this will be sigma P1 sigma minus 1 y and times the denominator minus P1 sigma y, and it will be 1 plus sigma P1 sigma. Have we done? Have we done the whole differentiation job here? Not yet. We differentiate this term and hold this. And then we hold this and differentiate this with respect to P1. So the whole thing has been done, right? The only thing we need to do, the last thing we need to do is to rearrange these terms. So this would be P1, 1 plus sigma, P2 to the power of 1 plus sigma. Okay, we have the same y here, so we have a y outside the parenthesis. And do we have P1? So we have this, and this would be P1 to the power of 2 sigma. So this would be P1 2 sigma. And we have P1 2 sigma. So we may have, okay, P1 to the power of 2 sigma, and once again, sorry, let me do it again. We just multiply it out, okay? So sigma y P1 2 sigma plus sigma y P1 sigma minus 1 and P2 1 plus sigma, right, minus 1 plus sigma y P1 2 sigma. So, oh, not this, this, and this. So something here will be cancelled. Is that right? Sigma yp to the power of 2 sigma. Sigma yp1 to the power of sigma. Alright? So we have a negative yp1 2 sigma here. Plus sigma yp1 sigma minus 1 p1, sorry, this should be p2, right, p2 1 plus sigma. And we can do something here. What can we do? Oh, hey. Let me rearrange this term into here. We may have y and p1 sigma minus 1 and negative p1 1 plus sigma plus sigma. Actually, we don't have to do this. Sorry. We don't have to do this because remember, remember sigma is a negative term, right? So sigma is a negative term, and here we have a negative sign, right? And the other parts are positive. Okay? So the whole term must be a negative term divided by a square thing, which must be positive. So the whole thing can be verified that the differentiation is negative. Okay, so have we already proved that the demand function of Q1 satisfies the law of demand? Yes, right? The higher the price P1, the lower the quantity demanded Q1 star. It's an inverse relationship, right? So all we have to do is to differentiate and rearrange the terms. Alright, I admit it's a kind of annoying thing, troublesome, quite troublesome, I think. But actually we can do this. And the last thing we'd like to check is about P2. Alright, so let me ask you the first question that we have already checked that Q1 is a function of P1 and their relationship is inverse, is negative. So do you think we need to check Q2, which is a inverse function of P2? Do you think we have to do this or not? Actually, we don't, right? Because these two functions are symmetric. They are symmetric. You may see the same form. Okay? So once we have checked that Q1 is a negative function of P1, so we may conclude that Q2 must be a negative function of, or an inverse function of P2. So both good 1 and good 2 satisfy the law of demand. The higher the price, the lower the quantity demanded. Okay, is that clear? Now the last thing, we'd like to check the cross effect. How the price of good 2 affects the quantity demanded of good 1. So the last thing we'd like to check is this. Partial Q1 star partial P2. If the result is positive, then we say good 1 and good 2 are substitutes or complement. If the term is positive, then we would say good 1 and good 2 are substitutes or complements. The higher the price of good 2, the higher the quantity demanded of good 1. So people just switch their choice from good 2 to good 1, right? As P2 goes up. As P2 becomes expensive, more expensive, then people will go to good 1. So we may reasonably conclude that they are substitutes, right? In this case, they will be substitutes. Substitute. They are substitutes mutually. But if this is a negative term, then they would be complements. Okay, so let's check. Now Q1, the result here. So we have P2 here. So this equals, you may regard this term as a term here, but to the power of -1. So P1 sigma y can be held, and it's a -1 with this term to be -2. So it's a P1, P2, not yet. And then it will be 1 plus sigma and P2 sigma to the power of sigma. Alright, so we have a negative term here. This must be positive, right? Price, a positive price. Income, positive. Price, a positive, so this must be positive. And positive, okay? So, do you think we have already verified that this relationship to be a negative one? Have we done this? Yes or no? Actually not yet, right? Because actually we have another term here, which is 1 plus sigma. And do you remember what is 1 plus sigma? 1 plus sigma equals rho over rho minus 1. And this must be negative, okay? But we are not sure whether rho is a positive one or a negative one. Okay? So if rho, we only know that rho must be less than 1. But rho cannot be 0. But rho can be here or can be here, right? So if rho falls within this area, this region, between 0 and 1, and then rho is positive, but rho minus 1 is negative. So that 1 plus sigma would be negative. So in this case, it's a negative, negative, so two negative make a positive, right? Double negative make a positive. So this would be positive. In this case, it would be substitute when rho falls within this area. Okay? But if rho is negative, less than 0, when rho is negative, rho minus 1 is negative. So double negative again. Double negatives make a positive. So this term would be positive. So it would be positive and negative, so complement. Okay, so I hope you may appreciate the beauty of CES. Because once again, remember in Cope-Douglas utility function, Q1 is a function of P1y, but not P2. Good 1 and good 2 are basically mutually independent, right? But here, for CES utility function, Q1 is actually a function of P1, y, and P2. So, a CES demand function is actually makes the good as a normal good and also satisfying the law of demand, and also these two goods can be what? Can be substitutes or complements. It depends on the value of rho. Okay? So when rho falls between 0 and 1, these two goods are substitutes. But when rho is a negative 1, when rho is less than 0, then these two goods would be complements. Is that clear? So CES is actually a good one to capture so many properties that we appreciate, right? But don't forget, to derive a CES demand curve, it's a little bit complicated to do that. Not that complex, but a little bit, at least a little bit more difficult than Cope-Douglas utility function, right? So Cope-Douglas is the easiest utility function to deal with, but CES actually is fine, and CES can give us a more better conclusion, more fruitful demand function here, okay? So the time is 9:55. Let's come back by 10:10. Okay.